So in the last topic, we met Newton's laws of motion, which described how forces and accelerations change the motion of objects. Now let's try some examples of using these laws of motion. Let's use some forces that we're quite familiar with. One that we see every day, one that we experience, one that's essentially inescapable for most of us. Let's start with the force of gravity. So let's look at our car. Imagine our car is now just sitting free in space somehow near the surface of the Earth. The only force that's going to be acting on it is the force of gravity. And we can draw that, as we draw most vectors, as an arrow, in this case pointing downwards. That's the direction of the force. And we can write that there as the force of gravity. Now this force, it turns out when you're near the surface of the Earth, is simply equal to your mass multiplied by a number that we call g. This number g we call sometimes the acceleration due to gravity, and again, as long as you're near the surface of the Earth, it has a definite value of about 9.8 meters per second squared. If the only force acting upon you is gravity, you're said to be in free fall. In fact, it doesn't matter if you're moving upwards or downwards or sideways. If the only force on you is gravity, you're in free fall. What does that mean? Well, let's apply Newton's second law of motion. We can write here that the net force acting on the object, which of course will be the sum of all the forces acting. In this case, there's only one. It's gravity because you're in free fall. We call mg, by the way, your weight. The force of gravity is called the weight. And that's going to equal the mass times the acceleration by Newton's second law. What we can do now is we can cancel the mass off both sides of this equation, and we find that our acceleration will now simply equal g. That's why we call the g the acceleration due to gravity. If the only force acting upon you is gravity, you will accelerate downwards at 9.8 meters per second squared. And of course, interestingly here, mass has nothing to do with it in terms of the rate of your acceleration. The larger your mass, the larger your weight, the larger your mass, the harder it is to accelerate you, and they cancel out. Now let's move on to another example with gravity, but this time our car won't be just sitting in the air in free fall, it'll be sitting on a surface. Now when our car sits on a surface, there's more than one force acting upon it. We can tell that because the car is no longer accelerating up or down. So we can draw on our car here, there's going to be a force of gravity downwards again. We'll call that mg. But there must be some other force acting because the car is not accelerating downwards. In fact, the net force on the car seems to be zero. The car is just sitting there. And we call that force from the surface that the car is sitting on, pointing in this case upwards, we call that the normal force, and we'll give it a letter n here. Now it's not normal in the sense that it's usual or typical, it's normal in that it's normal to the surface, and that's what we mean mathematically by at right angles to the surface. So a surface pushes on us at right angles to the surface. In this case here, Newton's second law is quite easy. We can again write down that the net force will add up all of these forces. Let's say that the normal force pointing upwards is a positive direction. That means the weight force pointing downwards must be a negative value. So there's our net force. And again, according to Newton's second law, that must equal mass times acceleration. In this case, that's going to be zero because our acceleration in this problem is zero. The car is just sitting still and not moving at all. Then we can rewrite this equation here to show us that n must equal mg. In this case, the normal force upwards exactly balances the gravity force downwards. Normal force equals the weight. Now it's important to realise here, although these forces are equal but in opposite directions, they're not an action-reaction pair like Newton's third law would tell us. Another way to tell that is to look at an example where the road is not horizontal. Let's look at an example where our car is on a road that's got a tilt to it. Now gravity will still act downwards as it always does. There's our weight force downwards. And again, the surface is pushing on the car, but the surface pushes at right angles to the surface. So in fact, the normal force here will point upwards in that direction. You can see here the normal force and the weight force will not be equal and opposite. They are not an action-reaction pair ever. In fact, in this example here, you can see the normal force will not balance the weight force. There will be a net force on this car. And of course, if these are the only forces acting, the car will have a net force that will in fact point down the slope. The car will roll down the slope. Now let's meet another force that we're often quite familiar with. That is the force of friction. We're quite familiar with that. In fact, this is one of the reasons why the standard mode of motion was thought to be coming to rest, because we find it hard to escape friction forces. Friction forces, it turns out, have to do with how hard the surfaces are pushing on each other. In the example I've shown here, and the car's kind of upside down because wheels don't provide a lot of friction, so I've put my car on the roof and we're going to try to push it along. If our car is moving in this direction here, for example, then the car still has its weight downwards, it will have a normal force upwards, and if there's friction between the two surfaces, there'll be a friction force acting opposite to the direction of motion. In this case, it'll be off in that direction there. The friction force actually depends upon the size of the normal force, and it equals some multiple of the normal force, which we use the Greek letter mu, and we call that the coefficient of friction. So the rougher the two surfaces are, the larger the coefficient of friction. The smoother the two surfaces are, the smaller the coefficient of friction. Now let's try an example using Newton's second law with the force of friction included. So here's our example. We have our car. We're going to try to push the car along at constant velocity. Our car has a mass of 1,000 kilograms, and the coefficient of friction between the car and the road, we're going to say here, is 0.1, quite a small value. So we know now that the normal force in this instance will equal the weight because it's on a horizontal surface. We also have been told in the problem that our coefficient of friction is 0.1. So we can solve this problem now by writing down that the net force on our car will be us pushing the car forward. Let's call that force of us. And there'll be a friction force opposing the motion, the force of friction in the opposite direction. So this will be our net force, as in the force from us minus the force from friction, and that will equal mass times acceleration by Newton's second law. And in this case, again, that's going to be 0 because the problem said we're going at constant velocity. So that now says the force that we have to push with will equal the force of friction. They're exactly balanced, and that's going to equal mu times the normal force, in this case 0.1 times 1,000 times g, which is 100 times g. It's the same force you would need to hold up a 100 kilogram mass. Quite a large force. Maybe you need someone else to come and help you push the car if that's the case. Now what we're going to do in the next topic is move away from using forces and accelerations and come up with an entirely new way of analysing motion problems that actually doesn't use vectors at all.